Some of the work that I'll be talking about today comes from a workshop report. We had a workshop here last October, and the title of the workshop was Bathymetry from Space, and I have a copy of the report with me, and I'll tell you at the end how to get it. But I've taken a lot of the nice graphics out of this report for the talk today. So I hope to explain what's in this report, why we want to know the bathymetry of the seafloor and how we know it and how we can do better. The title of my talk is Draining the Oceans, and first I'll talk about why the ocean basins are so poorly charted. Then a little bit about one of the early expeditions at SIL called Downwind. Then I'll talk about satellite altimeters. That's my main area of research, how we use these satellites to study the ocean floor, what their limitations are, and how we can do better with future satellite altimeters. Then a little tour of the deep oceans, looking at mostly plate tectonic features like spreading ridges and trenches and seamounts and so on. And then a little bit about modern seafloor mapping tools, multi-beam echo sounders, the kinds of things that Scripps has on their ships today. And then finally a little bit about prospects for the future in both the multi-beam side and the satellite altimetry side. I think both of these tools are needed to understand the ocean basins. Okay, so I brought a few videos with me today to illustrate what the ocean floor would look like if you could drain the ocean part off. So most of my research, I'm interested in the bottom of the ocean and not the ocean itself. And so here's an example. We're flying from outer space in toward the mid-Atlantic ridge here. This ridge is the spreading ridge between the North American and Eurasian plates here. And there's a ridge axis right here that's offset multiple times by transform faults. So this is the sort of standard view of the Earth from plate tectonics. We're going to fly up the ridge axis here over to Iceland and then stop up here. And I'll show you some more of these videos later on. Now, I'd like to contrast that with a view of Mars. What we know about Mars from orbital measurements from a laser altimeter around Mars. And actually what we know about Mars is a lot better than what we know about the Earth's oceans. Probably 100 times better. I'll show you in the next slide. So these are measurements of Valles Marineris made by the Mars Orbiting Laser Altimeter mission, and this laser flew over the surface of Mars thousands and thousands of times, measuring the height of the topography of the surface and creating this three-dimensional picture of the surface of Mars. And you see that it has really remarkable detail, a lot better detail than we have of the ocean basins. Valles Marineris is a canyon here about 7,000 meters deep. And of course, yesterday there was a launch of a new satellite to Mars, and I think the cost of that mission plus the next mission is about $800 million. So there's a lot of research money going into planetary exploration, and maybe not quite as much going into looking at our own planet. So this is part of my story today, is we need to study our own planet. Okay, just a quick overview of what we know about the topography of Mars versus what we know about the topography of the Earth. Here's Mars, Earth's oceans today. Not the topography of the land, but the oceans. The horizontal resolution we have from the Mars laser altimeter mission is about 2 kilometers. In other words, if you move 2 kilometers or about a mile, you get a new measurement of the topography of the surface of Mars. Earth's oceans today, on average, is about 25 kilometers. Not very good. There's a lot of the oceans that are uncharted, a lot of area. In terms of vertical accuracy, if you went to a spot on Mars where there was a laser altimeter measurement, you would know your height to a meter, which is just incredible, 3 feet. Whereas on the oceans today, we're still at the sort of 250 meter level. This is away from where we have ship measurements. This is out in the voids. So we know a lot more about Mars than we know about the Earth, which is sort of a sad state of affairs. Okay, why is this? Well, If you look at the distribution of where ships have gone in the last 40 years, and that's what this map shows, you'll see, first of all, there's a high concentration of ship tracks. Here we are in San Diego right here. You'll see lots of ships have come out of San Diego Harbor to go off and do exploration in other places. So there's a high concentration of tracks around here. Also, you go to places like Hawaii, and there's a very high concentration of ship tracks where people have measured depth and magnetics and gravity and all kinds of things. Tahiti also is another one. And also, if you go to the seafloor spreading ridges where the plates are spreading apart, there's a high concentration of ship tracks because this is an area of scientific interest, and there's been a lot of exploration of the ridges. But there are areas in the oceans where there's very little ship data. Here's a box here in the South Pacific, south of Tahiti, between New Zealand and South America. Now, if you took those ship tracks and superimposed them on a map of the U.S., you get the kind of ship track distribution that's available for studying the deep oceans in these areas. There's whole states that don't have one ship crossing of depth. And these are slides that I got from George Sharman at NOAA. And he likens this to trying to map the U.S. along the interstate highway system. So let's say you were just trying to map the topography of the U.S. and you only had data along the interstate highway system. What would you learn? There's huge gaps in our coverage. You wouldn't learn much about Nevada here. So this is one of the problems. There are areas in the world where the shipboard coverage is good, but there's lots of areas where the coverage is very poor. Okay, now I thought I looked back in the archives. There's, as I said earlier, there's a lot of things in the library about old Scripps expeditions, and this is one that I've been interested in. It's called Downwind, and it occurred in 1957 and 58 during the International Geophysical Year. And this is aboard the RV Baird and the RV Horizon. There were two ships involved in this experiment, and they sort of took parallel paths, and I'll show you what the paths are throughout the Pacific Ocean. Here's a picture of Bill Menard over here. Bill was the chief scientist on half of this expedition, and Bob Fisher was the chief scientist on the other half. And Bill is no longer alive. Bob is still working with us down the hill in GRD. So where did this cruise go? It started in San Diego, and then they headed south to the Clarion and Clipperton fracture zones to learn about fracture zones. Remember, this is way back before plate tectonics was really understood. So it was a mystery sort of what these fracture zones really were, how they were created, and this was part of Bill Menard's research program to understand these features. And I'll show you what they are in a minute. Then they went down to the Tuamatus. They got to 48 South. Then they headed back towards South America. That's the first part of the expedition, and I think they spent Christmas here in Valparaiso. Then from Valparaiso, they went back up the Peru-Chile Trench, explored the Nazca Ridge, the Salia Gomez Ridge, Easter Island, and then back to San Diego. And what they had with them were pretty much the same tools we have today. Bathymetry, dredging, magnetics, gravity meters, hydrographic sampling, seismics, and so on. Today our tools are, of course, digital and better, but it's basically the same idea they had back then. This shows a track of where that expedition went. And I'm only showing the part in the South Pacific here. So they started from San Diego, came down south here. There's two ships. I only have highlighted one of them. And they got to the Tuamatus, and then they stopped in Tahiti, went down to the Cook Australs, way down south here to the Pacific Antarctic Rise Crest, over here to back to South America, up the trench this way, back across the Salia Gomez Ridge, up the East Pacific Rise, and back to San Diego. And it was called the downwind because if you think about the wind direction, winds are mostly the westerlies in this part of the at these latitudes. So you're going downwind, and then you come back up this way, and you get the trade winds, and so you're still going downwind. So I guess you could save some fuel or something. Or okay, so I plotted this track on what we know about the oceans today because it's quite interesting, and I'll flip back and forth. Because you can imagine back then they really didn't know where they were going. They had these very crude maps of what the ocean floor looked like. They probably knew barely where the East Pacific Rise was. And so you can see how they were navigating their cruise to try to hit these and highlight these features. So here's their track superimposed on the topography. They came down here, they crossed this set of ridges here, which I'll talk about because they're very interesting. We call them the Puka Puka Ridges. They spent some time here doing some dredging. Then they went through the Tuamatus and the Cook Australs. Down here they found the Pacific-Antarctic Rise Axis, which is right here. This is the Menard Fracture Zone, which is named after Bill Menard. I guess he never got there on that cruise. I don't know if he visited his fracture zone. And then back across the Chile Rise. The little red dots here are where the earthquakes are. So they sort of highlight parts of the seafloor spreading center. We've got seafloor spreading between the Pacific plate here and the Nazca plate and the Antarctic plate. So there's three plates that come together. So you can see when they came back from along the Nazca Ridge, they did a nice job surveying. They got to the eastern microplate, which is this thing right here, and they sort of got off track. Maybe that's where they wanted to go, and then they got back onto the East Pacific Rise and crossed that several times. Now I'll show you in a few minutes a cruise that we did in 1993 to these Puka Puka Ridges, and this is the western part of the Puka Puka Ridges, and they crossed one of the major ridges right here. And I didn't know this until I went to the library the other day. They spent some time here and they did some dredging. Okay, so that's an example of how the seafloor was mapped up until the mid-'80s and '90s when some new tools were developed. The big improvements were in GPS navigation. That's really a major improvement right now. Knowing exactly where the ship is to, nowadays you could do it to meters or maybe less than that, maybe to inches. So that's one big improvement. The second big improvement is in multi-beam sonars, using a multi-beam swath to map a much larger area of seafloor than just a single point beneath the ship. So those are the improvements on the seagoing side. On the side that I've been interested in, there are things called satellite altimeters, and I'll talk about that next. They use a completely different technology to map the topography of the ocean surface, not the seafloor, but the surface of the ocean. And I'll explain how this works, but basically there are mountains on the ocean floor. I think I have a better example on the next slide. Yes. Okay, so here's your radar altimeter up here orbiting the Earth at about 800 kilometers altitude, sending out thousands of radar pulses per second, measuring the altitude of the satellite to about an inch accuracy. And then if you can track that satellite with some kind of a tracking system, knowing its height independently above some reference shape for the Earth, you can difference those two heights and get a height of the ocean surface. Now, why do we care about the height of the ocean surface? Well, the ocean surface is nearly an equipotential surface of gravity. So in other words, you don't ever go up or downhill when you're on the ocean. You're always at the same sort of level. But there are bumps, and there are bumps and dips in the ocean surface that reflect things on the ocean floor. For example, if you have a large seamount on the ocean floor here, it has an extra gravitational attraction that'll pull the water towards it and pile that water up on the ocean surface. And that seamount might be 1,000 meters tall, 3,000 feet, and it will pile the water up about 3 feet high. So that 3 feet is spread over a distance of, 50 kilometers, 30 miles. Well, I shouldn't have put this slide in, but point here is that I didn't have a better slide. The point is that we want to measure things to 1 milligal. A milligal is a unit of gravity. It's about 1 part in a million of gravity. And you want to measure the gravity field to 1 part in a million. And you can translate that into how accurately you need to measure the ocean surface height. And you need to measure the ocean surface height to about 1 centimeter, less than an inch, over a 10-kilometer horizontal distance. That's a really demanding measurement, especially when there's waves on the ocean that are 2 or 3 meters tall. So this is a real technological challenge, and we haven't gotten all the way to this measurement yet. We're now at about 3 centimeters. There have been lots of these satellite altimeters put into space. There's 4 of them up there right now, all measuring a different thing. You can put these satellite altimeters in 2 types of orbits. You could put them into an orbit where you get nice coverage of the ocean surface. Here's Hawaii. Here's sort of complete coverage of the ocean surface from a satellite called GeoSat. There's been another satellite that the Europeans launched called ERS that also has good coverage. Oh, I should point out, this was a Navy satellite that launched back in 1985. So that we have these 2 data sets that have nice coverage of the ocean surface, but most of the satellite altimeters have tracks that repeat, and they just go over and over the same spot over and over again. And they're there to monitor the changes in the ocean surface height associated with currents and tides and eddies and so on. And so I would say 80% of all the work on satellite altimetry has gone into looking at changes in the ocean surface. And what we're interested in here are these mapping missions. And there's very limited data sets. There's 1 year from each of these satellites. So I won't go through all the theory, but what you do is you take these measurements of the ocean surface height and process those in a way to make these gravity anomalies, which are the variations in the pull of gravity. And then we take that and combine it with ship measurements of depth and make depth maps. And so we really need 2 types of data to do this. We need the satellite data and the ship data and combine them together. And we make something called predicted depth. And these predicted depths will be good where we have the ship measurements, but they'll be pretty much interpolated from a satellite measurement where there's no ship data. Okay, now what do we expect to see? The main thing that came out of this type of research was you could see plate tectonics beautifully. We have this plate tectonic theory that's developed from ship measurements all around the globe, but the measurements are very limited, and it's almost hard to imagine people could develop the theory based on such limited data. And the theory says that there are these rigid plates, and they behave rigidly, and you have ridges, seafloor spreading ridges, transform faults, and subduction zones, 3 types of plate boundaries, and that's all there is. It's very simple. That's what the theory says. But in fact, it really is that simple. You look at the satellite altimetry data, and it shows you this fabric of plate tectonics exactly the way you put it in a textbook. So it's sort of a remarkable discovery from satellite altimetry. It's not a discovery, it's just a confirmation of what people already knew. So the 3 types of boundaries again are the seafloor spreading ridge axes. This is where the plates are moving apart. You've got the transform faults where the plates are sliding past one another laterally. And then you've got the subduction zones where the plates are being consumed and subducting back into the Earth. So I'll take you on a tour of the Earth, keeping these features in mind and looking at how these features are expressed on the ocean floor. Oh, a really important aspect of seafloor spreading is that the seafloor seems to spread into 2 modes. If you go to the Atlantic Ocean basin, where the seafloor spreading rate is rather low, you get very rugged looking seafloor, and where the plates are spreading apart, you get an axial rift, a deep rift right here, several thousand meters deep. If you go to the East Pacific rise axis, where the seafloor spreading rate is higher, you see something completely different. The seafloor is rather smooth on the flanks of the spreading ridge, and you get a small axial high right at the ridge axis. So there are these two sort of completely different modes of seafloor spreading, and they create seafloor topography that's quite different. And we're learning today this affects how the ocean circulates and mixes and so on. And that's all part of this workshop report, how these differences in the roughness of the seafloor affect what's going on in the water column. Okay, so the first movie is an exploration of all the spreading ridges. So we're starting here in the Atlantic at a relatively slow seafloor spreading ridge, going down to the South Atlantic along the ridge axis here. You see ridges and transforms, ridges and transforms. We're getting down here towards Antarctica. Africa is right here. That's the tip of Africa. Here we're coming into the Indian Ocean and going to a very interesting place called a triple junction, where you have three plates meeting, and they meet exactly as predicted by plate tectonic theory. The geometry works out. The plates are spreading at the right speed. It's really a remarkable thing. Now we're going south of Australia, and we'll be coming up along the Pacific Antarctic Ridge across some major fracture zones here. Here is the Menard fracture zone. And then we're going up the East Pacific Rise axis by the eastern microplate, and we're going to end up back here in the Gulf of California near San Diego. So we're coming up here along the East Pacific Rise and then ending up in the Gulf of California. Okay, so that's sort of a tour of the ridges, and you can see there were two different types of ridges. There was the slow spreading ones where you had the axial rift, and then you got into the Pacific plate and where the spreading rate was higher and you get an axial high. And people still don't completely understand why that's true. I mean, they understand the spreading rate part, but they don't understand the physical connection. The next movie, we're going to fly across the Pacific Ocean between North America and Hawaii over here. And these are the big fracture zones that Bill Menard studied. He didn't understand what these were early on, and later on learned and understood how they were related to plate tectonics. But what we're doing is we're flying to the Aleutian Trench here. So here's Alaska, here's the Aleutian Islands, and here's the trench axis. And this is the place where, if you remember, the plates are getting subducted back into the Earth. So you get a deep ocean trench along here. And there's a flexural outer rise where the plate is getting bent and sort of flexed before it goes into the trench. Okay, so if you could take a satellite altimeter, you make a map of the topography of the ocean surface, and then you could just illuminate that, and illuminate it in a computer. But if you could illuminate it with the sunlight somehow, and get rid of all the waves, this is exactly what the ocean surface would look like. It's not flat. It's got all these funny little bumps in it, bumps and dips and things all over the place. And they represent the seafloor spreading ridge axis again. But what you see off the ridge axis are lots and lots of seamount chains, volcanic chains, including ones that we know a lot about. Tahiti, here's the Marquesas, the Cook Austral chain, the Tuamotus are here. Easter Island is over here. And here's the Galapagos up here. And even today, people don't completely understand how all these seamount chains form. There's hotspot models, there's stretching models, there's different theories about why these volcanic chains formed. And so what I'll talk about next is I'll talk about a survey that we did back in 1993, a number of us here at Scripps, investigating one of these seamount chains. And the reason for going there was not just to understand how the seamounts form, but the satellite altimetry showed us something that that we still don't understand. If you look at the gravity field over the Pacific Ocean, you see the normal plate tectonic fabric that you expect. But then you see these things called gravity rolls. And you can sort of see them here. They're these long features heading off in this direction. Here's the East Pacific rise axis. And they have small amplitudes. And they go in the direction of the absolute plate motion. This is how the plates are moving over the surface of the Earth. And so when the first satellite altimeter data came out from Bill Haxby and the people at Lamont, they discovered these gravity rolls. And there's been a series of cruises out to investigate these rolls and the volcanic features that occur nearby and on top of these rolls. Actually, they occur in the troughs of the rolls. So theories for why the rolls exist and how they're related to the seamounts, there's a variety of theories. The original one was that there were small-scale convection patterns in the mantle beneath the plates, and these caused undulations in the topography of the Pacific plate, and then you get a volcano up on the top here. But what we're observing now is that the volcanoes don't occur on the top of this gravity thing, they occur down in the trough. And so people have proposed this extension idea where the plates are extending and you get cracks in the plate and volcanism above the cracks. And then more recently there's another idea about thermal contraction, how the plates are contracting and cracking and bending and so on. Okay, so back in 1993, a number of us went on an expedition called the Gloria Expedition on RV Melville, and Jerry Winter, Jacqueline Memorex, a host of students. Stu Smith is here. Ron Comer was on that cruise. Captain Desjardins, I think, was the captain. And at that time, we had just had a new multi-beam sonar system on the ship. And so we had the opportunity to take this out and map the seafloor around these Puka Puka ridges. So the objectives were mainly for mapping and dredging, sampling rocks from the ridges, trying to understand the age progression along these ridges. So our survey line went like this. Here we are starting in Tahiti, and we went out to hook up with these Puka Puka ridges and follow the ridges down one of these gravity rolls and then back up, surveying with a multi-beam system and all the other instruments on the ship, dredging along the way. Now, as I said earlier, this ridge, this downwind expedition was really one of the first ones to cross this ridge and explore it. And they crossed over here near an island called Puka Puka. This is a ridge that doesn't come to sea level, so it's an entirely submerged feature. Okay, so the multi-beam sonar provides a swath of bathymetry beneath the ship out to angles of about 60 degrees from the vertical. And when you're in water depth of, say, 5,000 meters, that swath will be almost 20 kilometers wide. And so you can drive around mapping the ocean floor with this swath bathymetry, and it's sort of like mowing the lawn because you'll drive back and forth, trying to hit the features that are of interest. Now, with the satellite altimeter maps, you can say, well, based on the rather crude satellite altimetry, we now know where to drive the ship, and so you can be very precise in knowing where to do your ship survey. So here are some of those data. These are maps of the ocean depth, and you can see large undersea volcanoes like Puka Puka Island, Napuka Island. Here's the ridge that was visited by the downwind expedition, and there's one that we discovered is rather tall called Wahoo Gio. Comes up to less than 300 meters of depth. The normal depth here is about 4,000 meters. So Wahoo Gio, it's just a giant volcano sitting out in the middle of nowhere. It's a little bit ridge-like. You see it's connected to these other ridges. And one night we drove right over the top of it. It was sort of fun because we sort of knew from the other surveys where the seamount was, and then you could drive right over the top of this thing. The depths are coming up. You're hoping it doesn't come to zero. Going full speed. Okay, along this set of Puka Puka ridges were some other interesting volcanic ridges. And based on these kinds of observations, people are coming up with models for how these things formed. And one of the primary candidates now is this thermal contraction model. The plates form at the ridge axes. They start to contract. As they contract, they crack like glass or something as you cool glass. And so there's these ridges or volcanic chains that form in the cracks. Okay, now the rest of the talk I'll just talk about how we can do better in the future. Why don't we just go out with ships and map the world's oceans? It's a good question. It could be done, and it could be done at about the cost of one of these Mars missions. But it seems unlikely that it's going to happen. There's political reasons, there's military aspects to this, and so on. And it would take a long time to do it. About 125 ship years to map the deep oceans. If you just concentrated on the deep parts, actually it's easier to map the deep part because the swath of your sonar is wider. And so it would take about 125 ship years. Of course, you could do it in 10 years. It's 12 ships, It could be done. This shows the current publicly available multi-beam data sets that have been collected by oceanographic institutions and sent to NGDC, where they store all the data. And you can see the coverage of the oceans isn't very good. It's not there isn't more data than this, but this is the publicly available data, so people still haven't sent their data to the archives. But at the rate we're going, we're never going to map the ocean basins with ships. This graph is a little hard to understand, but I'll just explain what's going on here. If you wanted to map all the oceans with ships all the way up to the coastline, so you go in 100 meters of water, it would take about 918 ship years to map all the oceans with ships. If you want to focus just on the deep oceans, greater than about 2,000 meters, it would only take that 125 ship years. The problem is when you get into the shallow water, the swath of the sonar gets narrower and narrower. You have to do more and more tracks, and it becomes really difficult. So another way to do this would be to map the deep oceans using satellite altimeters. I don't know what we do in the shallow oceans. There's other problems, political problems. You can't get into people's territorial waters and so on. But the deep oceans, at least, you could do with ships, or you could do it with satellites. So again, here are those two technologies. Here's the multi-beam sonar. It maps the swath about 20 kilometers wide. Here's the satellite altimeter. It gets global coverage, but it can only resolve things about 10 kilometers wide. So they're a pretty good match here. You got one that gives you the large scale stuff, and you got one that gets you the small scale features. I'll explain a little bit about why satellite altimetry can't resolve things you can resolve by a ship. And there's just some basic physical principles. And the first one is just that you're measuring the gravity field on the surface of the ocean, and you're trying to infer what's down at the bottom of the ocean, and there's this big thick water layer between you, and the gravity field gets smoothed on the way up, and it loses all of its short wavelength information. It's called downward continuation or upward continuation, depending on what direction you're going. The ocean waves, remember I said before, you want to measure a centimeter height difference over 10 kilometers horizontal distance. The ocean waves are several meters. So you've got to take thousands and thousands and thousands of measurements to beat down that ocean wave height noise and get to that 1 centimeter accuracy. And then in the shallow areas we have tides. We still don't know the tide models very precisely. Again, the ocean waves are only a problem mainly in the southern hemisphere where you have lots of waves. And here's a map of the wave height averaged over a year over the globe, ranging from 1 meter to 5 meters. And on average, you get lots of large waves down here around the Antarctic circumpolar current. And so this is going to be a problem area always to doing anything. Even going out on a ship, you don't want to go out on the ship in that area because the waves are so high. So it's a difficult area to work in. But you can see that the errors in the satellite altimeter measurements are perfectly correlated with these wave height errors. So we need some improvements to beat down the wave height errors. And we're approaching that on two fronts. We're going back and looking at some of the older data to try to clean it up, reprocess the data, improve the accuracies of those measurements. And we're making some progress there. Here's an old version of gravity, and now we're retracking some of the data and cleaning up the images and being able to see the specific rise axis, and this is the Cocos Ridge here. What we're trying to achieve here with the altimetry is to see something called abyssal hills that I haven't talked much about. But when you have seafloor spreading, it spreads in little pulses, and every pulse creates elongated hills that are parallel to the seafloor spreading ridge axis, and the scales of those are pretty small, less than 10 kilometers. But those turn out to be the parts that are important for studying ocean mixing and deep ocean circulation and so on, that roughness of the seafloor due to the abyssal hills. And so if we could only see the abyssal hills with the satellite altimeter data, we could then estimate the roughness of the seafloor globally around the oceans. And so we're just barely getting there. Here's the seafloor spreading ridge axis in the South Atlantic, transform and so on, ridge transform, ridge transform. You see, it's beautifully, just as plate tectonic theory would predict. It's absolutely perfect. And then you see these things that are symmetrical on either side of the ridge. These are wonderful things for trying to understand how to put the plates back together, because you know that at one time those were back in the same spot at the ridge axis. And then if you squint, you can start to see these hills that are parallel to the ridge axis. So they're just becoming visible in the altimetry. Now, the other approach is to launch a new satellite mission, and we're sort of preparing to do this now. We had this workshop that I talked about. We're trying to gather up all the science that can be done with such an instrument, and then trying to sell this idea to NASA and NOAA and the Navy and whoever will help pay for a new satellite mission. So I'm taking donations right now. So. And the key to this satellite mission is to improve the ranging technology. Johns Hopkins Applied Physics Lab has really developed all these satellite altimeters, and they have a new instrumentation now that can beat down this wave height noise by a factor of 2. So that's getting us part of the way to our goal here, this factor of 2. And then the other thing we want to do is have this new satellite altimeter mission go into space for 6 years. We only had 2 years of data so far. If we get 6 years of data, we could beat that noise down by a total of a factor of 5 and really pick up some of the subtle details of the ocean floor. So in 6 years, you can get a really incredible track distribution. Here's some tracks around Hawaii. These are hypothetical tracks from a new satellite mission compared with what we have now. As I said early in the introduction, we had a workshop here back in October where we gathered about 50 scientists to bring their science issues to the table and see how those can map into a new satellite mission. And I have a workshop report. It's at this web address. In fact, almost everything you saw today can be found at that web address. Go out there and you can find maps of the ocean floor or gravity or explanations of how the gravity is created and that kind of thing. So in this workshop report, we've identified numerous applications of this technology. It ranges from doing sort of climate studies to ocean mixing to the seafloor mapping and marine geology that I talked about today, to things like laying fiber optic cables, knowing where you want to lay that cable so you can avoid some of the tectonic features or slides. There's things on the law of the sea, understanding where the 250-meter isobath is. That turns out to be an important issue nowadays because countries can claim territory based on where that isobath is offshore. And so just understanding where that isobath is has become a big deal. Petroleum exploration industry is really interested in this technology because it helps them map the continental margins. Now they're exploring for oil, often in much deeper waters, and they have almost no types of information. So they use this as a reconnaissance tool to go out and then do their more detailed ship surveys. So again, I'll try to sell you a mission here. This is all we need. It's less than $100 million. Just think of it in terms of a Mars mission. It's only 1/8, you know. It's hardly anything. So we need improved range precision. We need this fine spacing that can be gained by putting the satellite in orbit for 6 years. And there's some other things people would like: to be able to go closer to shore, to understand the gravity field all the way up to the shoreline for these exploration activities. So I think that's it. If there are any questions, I'd be willing to take questions. The question was, does measuring the magnetic fields around the mid-ocean ridges help you understand the topography, I guess? Well, the magnetics, of course, in the early days of plate tectonics were the key issue in understanding plate tectonics, because as the seafloor spreads, it records the present-day magnetic field in the crustal rocks, and that field reverses over time of millions of years, and so you can get the complete history of the seafloor spreading. There is a topographic part, and in fact on these seamounts that we surveyed, because they stick up so high, you can use the seamount as a generator of magnetic field to understand the polarity of the magnetics. But at the ridges, the relief is pretty low, so it's not a giant issue, but I think it is important. Question was, is there a big difference between the topography of the land and the undersea topography? Yeah, there's a huge difference. It's mainly because the seafloor is very young. It's less than about 70 million years old. That sounds old, but compared to the age of the continents, which are about 1 billion years old, it's young. And there's not much erosion. There's no erosion on the seafloor, like rivers and streams and water coming down to erode the topography. So what you generate at a seafloor spreading ridge is pretty much locked in and carried all the way to its death at the subduction zone. Although there are sediments that come down and flatten it out. Whereas you go to the continents and the topography is completely different. It's dominated by the erosional processes. The mountain building processes are pretty much obscured by all the erosion. So there are lots of differences. The question is, what's the difference between the Mid-Atlantic rise and the East Pacific rise in terms of how the continents have moved? Okay, what seafloor spreading tells us are the relative motions between the plates. It just says this plate has moved relative to that plate by a certain amount. And it's hard to get at the absolute motions. Like during that process, was Africa or the African plate fixed? That's sort of what you're implying. And it really is true. The African plate is sort of fixed. You have spreading on the southern Mid-Atlantic ridge, so the South American plate is moving to the west, and it's overriding the Nazca plate. And so, I mean, you're correct that there is this distinction between relative plate motions and absolute plate motions, but the rates are still different. The relative rates are different. I don't know if I answered your question, but okay, I'll try to repeat the question. No, I understand it. The question is, we're measuring the topography of the ocean surface, and there's two components. There's a permanent part due to gravity, and there's a part due to currents. And there can be very small currents over things like seamounts. And how do they affect our estimates of the depth? And first of all, we hope that those currents are not permanent. In other words, that they move around or shift around with respect to the seamount. So when the satellite visits that seamount, every time it comes over, it sees a little bit different current, and we can average the numbers and get back to the permanent number. But the other answer to your question is I think that those signatures are relatively small compared to the gravity part. If you look globally over the Earth, the variations in sea surface height are about 30 meters, plus or minus 30 meters. It's, a pretty big number. The variations due to the ocean currents are about plus or minus 1 meter. So the gravity part is dominating the whole measurement. Okay, the question is that you have a gravitational attraction of a seamount which causes a bump on the ocean surface. How far below the ocean surface does that gravitational perturbation disappear? It doesn't. It goes right to the bottom. So if you went down to the bottom of the ocean and you towed a gravity meter over that seamount, you would actually see a larger effect because you're closer to the feature. And so as you go up away from the seamount, that gravity effect gets smaller and smaller. So it's throughout the whole water column. It's a permanent gravity effect.
A couple more questions, and then I'm sure they will take them afterwards.
Yeah, the question is it possible that there are variations in the density in the crust that would perturb the ocean surface and mimic, and we'd interpret them as being topography when they're not? And yes, that's entirely possible. In fact, what the oil industry is interested in is you go up on the continental margins where the seafloor is relatively flat, and you still see variations in gravity, and those are reflecting variations in the density below, and what the basement structure is, and how you could understand sedimentary basins, where the basins are, and so on. So that's their primary tool for investigating these margins. So that's sort of the flip side of the measurement. Yeah. One more in the back. I guess if I understand the question is, if the plates are really rigid, why don't these transform faults and fracture zones just go right straight to the subduction zone? Well, there are plate reorganizations, and I guess you're right, there's non-rigid plate behavior, because as the plate tectonic system evolves, you could develop a new plate somewhere, and that'll change the spreading direction of all the other plates a little bit. And so you can evolve from a set of fracture zones that are going in one direction to a set of fracture zones going off in a different direction. And yeah, you're right, it's not exactly rigid behavior. There are these changes, but and that's something people are trying to understand.
Thank you very much, Dave.
Okay.